In this video, we're going to talk about nuclear chemistry. So a couple of terms related to nuclear chemistry. If you think way back to the very beginning of the semester, we talked about isotopes. So isotopes are atoms of the same element that have a different number of neutrons. So remember, if they're the same element, they have to have the same number of protons, because the number of protons is the identity of the element. But when we have isotopes, they have a different number of neutrons. In nuclear chemistry, we often refer to what we call nuclides. Nuclides are the nucleus of a given isotope. So when we refer to nuclides, we're talking about the nucleus of different isotopes of that element. So when we have an isotope, the way that we write the symbol for that isotope is we write the element symbol. So instead of X here, we would write whatever the element symbol is. If it was hydrogen, we'd write H. If it was carbon, we would write C, and so forth. So we would have the 1 or 2 letter symbol for the element there. And then at the top left, we write the mass number. So the mass number is the total number of protons and neutrons in the nucleus. On the bottom left, we write the atomic number, which is the number of protons. So the atomic number we can get directly from the periodic table if we're not given that. The mass number, we would need to know how many neutrons is in that particular isotope. So for example, if we have something like uranium-235 or uranium-238, we can figure out how many neutrons are in that element. We know if it's uranium, we're always going to have 92 protons because uranium has an atomic number of 92. So for example, for uranium-235, if we take the 235 minus 92, we get 143 neutrons. For uranium-238, if we take the 238, which is our mass number, and subtract 92 protons from that, we get 146 for the number of neutrons that we must have in that isotope. So when we have a nuclear reaction, we are referring to a type of reaction where we have a decomposition of an unstable nuclei. So if we have a large enough nucleus, especially once we get above about lead or so, those nuclei become so large that they're unstable, and they will spontaneously break down into smaller elements. For example, if we have radon, which has an atomic number of 88, if we release a helium nucleus, so if you look at helium on the periodic table, it has an atomic number of 2, and most isotopes of helium have 2 neutrons, which means it has an atomic number of 4, a mass number of 4. If we lose a helium nucleus from that, 88 minus 2 gives us an atomic number of 86, and 222 minus 4 gives us a mass number of 222 left. So remember, our mass number is protons plus neutrons, so we have a total of 222 protons and neutrons left, and a total of 86 protons left. If you look up 86 on the periodic table, you will find that is radon. So this is an example of an unstable nucleus because we have such a large nucleus breaking down into smaller nuclei to be slightly more stable. When this happens, we say that we undergo radioactive decay. So radioactive decay is when a nucleus undergoes decomposition and it forms a different nucleus as a result of that. So we're going to look at some examples here of radioactive decay. So one type of radioactive decay is when we release alpha particles. So the symbol for alpha particles is this Greek letter alpha here. Or sometimes we will use the helium nucleus to represent an alpha particle, because that's what an alpha particle actually is it's a high energy helium-4, and there should be a hyphen here, a high energy helium-4 nuclei. So if you think back to what we were talking about in the last slide, helium has an atomic number of 2 and a mass number of 4. If it has a 2 positive charge, since it has 2 protons, it would only have 2 electrons. If it loses those 2 electrons, the only thing we actually have left is the helium nucleus. So when we undergo alpha decay, meaning we lose an alpha particle, one of our products is going to be a helium nucleus. And if you think way back to the beginning of the semester again, remember the law of conservation of mass. So the law of conservation of mass tells us that we cannot create or destroy matter. Let's see if I can fit that in here. Create or destroy matter. So if we lose a helium nucleus, then we have to have what's left make up the remaining protons and neutrons. So if we have 88 protons on the left side of our equation, and we've got 2 here, then we can only have 86 left, because 2 plus 86 would give us 88. So if I take 88 minus 2, that gives me 86 protons left. And if I take 226 minus 4, that gives me 222 protons and neutrons, or our mass number there. And then if I look up 86 on the periodic table, I find that that is radon. So let's take a look at another example here and write an equation ourselves. So we want to write the equation for the alpha emission of uranium-238. So 238 is the mass number. Whenever you see an element written this way, the number that follows it is the mass number. And we're not given the atomic number, but we can look on the periodic table, and uranium has a mass number of 92. So we want to write alpha emission. So alpha emission and alpha decay mean the same thing. We're going to release an alpha particle. And we know that an alpha particle is a helium nucleus. Sometimes we leave off the 2 positive charge there, and it's just understood to be there. So if I do that, I need to figure out what my other nucleus is. So I have to conserve matter, which means that whatever is left over has to be the remainder of this nucleus. So 92 minus 2 would give me an atomic number of 90 left. And 238 minus 4 would give me a mass number of 234. So then I can look on the periodic table and find out what element has an atomic number of 90. And since we've already found uranium, if we just go 2 back from that, we find that that is thorium. So when I have uranium and it undergoes alpha decay, I get thorium-90 as a result of that. So another type of radioactive decay, we release beta particles. And the symbol that we use for beta is the Greek letter beta. Or we can represent this as an electron, because that's essentially what a beta particle is it's a high energy electron. So what happens is that a neutron decomposes into an electron and a proton. the electron gets ejected and the proton stays in the nucleus. So for example, if uranium-235 undergoes beta decay, I have my beta particle here, which is an electron. So an electron, if you think back to when we talked about protons, neutrons, electrons, and their relative masses, the electron is so small that we consider its mass to be negligible. So it does have some mass, but it's just so small in relation to a proton or a neutron that we consider that mass to be negligible, so we say it's 0. So if we take a uranium atom, or uranium nucleus rather, and we eject a beta particle, 92 minus a negative 1. So in algebra, when we subtract a negative, we're essentially adding something. So 92 minus a negative 1 really becomes 92 plus 1. So 92 plus 1 would give us 93. Our mass number doesn't change since this electron is so small that the mass is negligible. And if we look up atomic number 93 on the periodic table, we find that we have neptunium. So let's try an example here. We have lead-210. And if we look up lead on the periodic table, lead has an atomic number of 82, rather. And we are going to emit a beta particle. So I'm going to go ahead and write my beta particle and then figure out what my other element would be. So 82 minus a negative 1 would give me 83. And my atomic number doesn't change since my electron's mass is negligible. And if I look up 83 on the periodic table, I find that that element is bismuth. So another type of radioactive decay is gamma radiation. Gamma radiation is essentially high-energy electromagnetic radiation. So it's not really a particle, it's actually a form of radiation. So if we think back to the electromagnetic spectrum, if you look at the electromagnetic spectrum in that diagram of the radiation wavelengths, what you'll find is gamma radiation is actually listed on there. Gamma radiation is an electromagnetic wave. It doesn't actually have any mass. And we use the symbol gamma, the Greek letter gamma, to represent gamma radiation. So if you see gamma radiation, sometimes you'll see just the symbol for gamma. Sometimes you will see the zeros there because it has no mass and it doesn't change the atomic number either. This will usually be listed somewhere in the equation as a product, but a lot of times we have other forms of decay along with gamma decay. We also have positron emission. A positron is a high-energy electron that has a positive charge on it. So instead of a negative one, we have a positive one since this is a positron. So for example, if we have potassium, which has an atomic number of 19, 19 minus 1 would give us an atomic number of 18, and the mass number does not change. The element that has an atomic number of 18 is argon. So let's try an example with positron emission. We have xenon-118. So we have xenon, which has a mass number of 118. And if you look up xenon on the periodic table, you will find that it has an atomic number of 54. So if we do 54 minus 1, that's an atomic number of 53, and we have a mass number of 118. If you look on the periodic table, the element that has an atomic number of 53 is iodine. So the last type of radioactive decay that we'll talk about is electron capture. Electron capture is when a nucleus captures an inner shell electron, and that converts a proton into a neutron. So for example, if we have mercury, mercury has an atomic number of 80, and this particular isotope has a mass number of 197. So if we capture an electron, 80 minus 1, or in other words 80 plus a negative 1, gives us 79. And then our mass number doesn't change, so we end up with gold as our element. So let's take a look at an example of electron capture. So we have polonium-204. If you look on the periodic table, polonium has an atomic number of 84. And we're going to do electron capture, which means the electron is now reactive. So 84 plus a negative 1 will give us 83. And the mass number is still going to be 204 since the electron's mass is negligible. And if we look on the periodic table, the element that has an atomic number of 83 is bismuth. Okay, let's take a look at a few examples here. And what I would recommend that you do is pause the video here and try these using the examples that we've done so far. And then start the video back up and check your answers here. So we have carbon-6, carbon which has an atomic number of 6 and a mass number of 11, and it produces a positron. So carbon, and we get a positron, which is a positively charged electron. 6 minus 1 is 5. Mass number stays the same, and if we look up an atomic number of 5, we get boron. Next we have bismuth-214 produces a beta particle. So a beta particle is an electron, a high energy electron. 83 minus a negative 1 is 84. Mass number again doesn't change since the electron's mass is negligible. And if we look this up, the element with an atomic number of 84 is polonium. The last one we have here, neptunium-237, produces an alpha particle. So 93 minus 2 is 91. 237 minus 4 is 233. And if you look up an atomic number of 91, you will find that what we get is protactinium. So we're way down the inner transition metals there. Okay, so this table summarizes the different types of radioactive decay. So we have alpha emission, we emit essentially a helium nucleus. We have beta emission, where we emit a high energy electron. Gamma emission, which is where we emit a gamma ray. Positron emission, so we emit a high energy electron that has a positive charge. So it's like an electron, but it's positively charged. And then we have an electron capture, where we capture an electron and a proton becomes a neutron. So this is a diagram here to show you a little bit about the different types of radioactive decay and how easily they're able to penetrate different things. So for example, if we have an alpha particle, it can't even penetrate our piece of paper here. It's stopped just by the piece of paper. If we have a beta particle, it has enough energy that it can travel through something like paper, but it would be stopped by a 0.5 centimeter block of lead. The gamma ray, though, actually has enough energy to get through the paper and the 0.5 centimeter lead. We would need a 10 centimeter block of lead to be able to stop the gamma rays.